Okay. So we won't discuss. I haven't sent you any problems for this seminar because my plan is the following. Plan for today. Today. So first hour will be I will explain the notion of construction of a Lie algebra of a group, of a Lie group. Lie group. So this will be first hour and 20 minutes. And the second hour and 20 minutes, or maybe less, well, I'm going to do some recast of linear algebra, namely tensor algebra, like tensor product of vector spaces, exterior algebra, tensor algebra, and I'm going to apply this construction to vector bundles of vector bundles. So I believe that the second topic is familiar for many of you. So it will be sort of either, well, you can just skip it, or well, in any case, it's something that belongs to undergraduate linear algebra actually course, but I'm going to use it heavily next time. So I decided to recall some basic constructions here. So and next time we'll have a problem session. I will send you some problems in advance. Let's start this lecture proper. So last time we discussed vector fields, and in particular one parameter subgroup of diffeomorphisms associated with vector field, and reinterpreted the notion of Lie bracket of vector fields in terms of Lie derivatives. And I'm not going to, and today I will use all these ideas heavily to explain really a key construction in the theory of Lie groups. So, well, a Lie group, so let G be a Lie group, so that means that we have a group together with a smooth structure on the underlying set G, such that the multiplication map and also the inverse map, which I will call I, from G to itself, that takes element G to G inverse, and this is multiplication. These two guys are smooth. That's the requirement, right? So smooth. And I will, to fix some notation, I will denote by E the neutral element in this group G. Okay, so a Lie group is a very complicated nonlinear object. So it has in general, classification of smooth manifolds is an incredibly difficult problem. And here you have a well, two structures. You have a set with two structures, multiplication and a smooth structure. They're somehow related, but still it's incredibly complicated object. And so the main idea of the whole theory of Lie groups is that one can associate to a Lie group a much simpler, a linear algebra object, which consists of, which is called the Lie algebra, which is just a finite dimensional vector space together with a skew symmetric map from this form on this vector space is valued in the same vector space, satisfying certain property called the Jacobi identity. So this is really an object of a finite dimensional linear algebra. It has no analysis in it, right? And the main discovery, which goes back to Lie and then elaborated by Cartan, Andre Weil, and Hermann Weil, and many others, that this finite dimensional linear algebra object remembers a great deal of information about the Lie group. So it's not true that this is really kind of a one-to-one correspondence between Lie groups and Lie algebras, but there is a, well, really, I will state later precise theorems how much Lie algebra remembers of Lie group. So the subject of my lecture is I'm not going to kind of construct for you sort of the inverse map or anything like this. It's really subject of another course. I'm just going to explain for you this error here, right? And the meaning of this sentence, Lie algebra. So and I will only state some precise results about the connection between these two sort of categories. Okay, that's the plan. Okay, so in order to define this promised linear algebra object associated to a group, so let me make the following definition, or maybe first a bit of notation. So notation. So let's consider for an element of a Lie group G, let's define a map which I will denote by L sub G, from G to itself, which is just translation by G, left multiplication by G. L G of G prime is equal to G times G prime. So L here stands for left multiplication. I could also consider right multiplication will be R sub G. Okay, so this map is smooth, and it's smooth because you can think of this as a composition of embedding of G into G times G, closet embedding with this multiplication. And using smoothness of M, it follows that this map is also smooth. Okay, so now so this L sub G is a diffeomorphism diffeomorphism of the underlying smooth manifold G, right? So now a key definition is the following. So a vector field, well, so I will call it theta, and let me use the following notation for the space of all vector fields on a manifold, vect G. So the space of all vector fields. Right? So a vector field is called left G invariant if the following is true. So recall that diffeomorphisms of a smooth manifold act on this vector space of all vector fields. So if so I consider this diffeomorphism, I consider my vector field theta, and I can apply this diffeomorphism to theta. And it's left G invariant if for any G, I get the same vector field. If for any G, in G, I have this. Okay, so let's try to let me sort of try to unravel the meaning of this equality. So, well, what does it really mean? So you have so what is a vector field? So you have I will draw a picture. So this is my manifold G, right? So I have and for every point I have the tangent space T, say G prime G. So this is point G prime, and right. So now, so the this map left multiplication by G takes this point G prime to G times G prime, and so I have the corresponding tangent space at point G times G prime, right? So there is a map, this map L sub G, that takes this point to this point, but it's differential maps the corresponding tangent spaces, right? So in fact, because L sub G is a diffeomorphism, it identifies the differential of this translation map, identifies the tangent space at point G prime with the tangent space at point G times G prime. This is an isomorphism, okay? So now, so what is a vector field? A vector field is a rule that assigns to every element of my manifold, to every G prime, an element of this of the corresponding tangent space, right? So in particular, I have a vector. I have a vector theta G prime, which sits here, and I also have a vector theta G times G prime that sits here. So, but as I already explained, this differential of the translation identifies these two vector spaces. So you may ask whether under this identification, this vector goes to this vector. In general, this need not be the case for an arbitrary vector field. And my claim is that saying that the vector field is left G invariant is precisely is equivalent to the following. So I will write it down. So theta is left G invariant if and only if for any G the differential applied to this vector is equal to this. Okay. So that's how the effect of this diffeomorphism is on theta is defined. That's merely a reformulation of the definition. Okay, so let's look again at this this formula here. So so in particular, you see that if you know the value of G invariant vector field at one point, at any point, for example, at point G prime equal to the neutral element E, then this formula recovers the value at any other point, right? So the sort of key observation here equation is that the map that assigns a vector field theta just one vector, its value at one point is the neutral element in my group. So this is a vector which belongs to T of G, defines an isomorphism of vector spaces. Spaces of left invariant G invariant vector fields on G and T E of G. So this is a finite dimensional vector space. So the vector space of all vector fields on G is definitely it's enormous, right? It's actually a module over the algebra of all smooth functions on G, right? If I have a vector field, I can multiply it by any function and get another vector. So this space is enormous. However, if I consider the inside this space a subspace of G-invariant vector fields, it turns out that this subspace is finite dimensional, and it's actually naturally isomorphic to T sub G. Just evaluation at one point. In fact, I could replace E by any other point, but it's convenient for me to take for the neutral element. So why this is the case? So I define for you this a map in one direction, right? If I have any vector field, I can look at its value at E. So this works not only for G-invariant vector fields, but for all vector fields. So, but now my claim is that a G-invariant vector field can be recovered just from this one vector. And this follows immediately from the formula that I have here. So namely, so the sort of the inverse map, takes a vector in T E sub G, a tangent vector, to to the following vector field theta, which sends G to theta G equal to differential of the translation at the neutral element applied to theta, right? So just look at this formula here. So you know that we know that if theta happens to be G invariant, then let's just plug here G prime equal to E. Then we get that theta G is equal to this differential applied to theta E. So theta G is recovered from theta E, right? Geometrically, it should be pretty clear because all this translation maps identify the fibers of the vector bundle or the tangent bundle, and so sort of saying that the vector field is G invariant is equivalent to saying that it's sort of constant with respect to this identification, right? If I, what you do, so you take for G prime just the neutral element, and then you use these maps to produce vectors in every tangent space, right? So, of course, so this definitely defines a section, just this formula defines a section of the tangent bundle, and I will leave for you, well, it's a very important exercise. Show that this map theta is smooth, right? So a priori, this formula here defines, well, for every element G of the group, it defines a vector in the tangent space. So it's not a priori clear that this map is even continuous, right? But I claim that in fact it's smooth. And so this is not a difficult exercise. It's but again, it's very important. So so we have the space of G invariant vector fields. We have a linear map from this vector space to T sub G, to tangent space at the neutral element, so just evaluation. And so if you believe to the exercise that, so the formula here defines a map backwards. So I claim that this theta sub g is actually a left G invariant vector field. So there is something to check here, because so by the very definition of this theta sub g, the formula here holds for G prime equal to E. And my claim is that if you know that this formula holds for G prime equal to E, then it follows automatically that it holds for any G prime. And that follows from sort of the fact that from the chain rule, basically, that the derivative of composition of two maps is equal to composition of the derivatives of differentials, if you use sort of another terminology. Okay, so so we have to summarize again. So we have a finite dimensional vector space whose dimension is equal to dimension of G, and we can identify it with a subspace of the space of all vector fields. Okay, so let me let's see here. So let me give you a few examples to see how it works. So I will give you 3 examples. So example 1 will be, I will take for G the group of real numbers. Of course, the operation is the addition. So let's try to understand what are the invariant vector fields. So, well, here, left invariant and, well, right invariant is the same. So group is commutative. I claim that invariant vector fields on G are of the form, it's quality, are all of the form G over dx multiplied by a constant is real numbers. So, well, from this very general claim that the space of G invariant vector fields is isomorphic to the tangent space, we know that this space must be one-dimensional. So, so basically the claim is that this is also a one-dimensional space. Basically, the claim is that all these vector fields are G invariant under translation. So let me maybe give you sort of a, I should maybe draw a picture for you. So what does it mean? So sort of what, here is another way of thinking about invariant vector fields. So what is a tangent vector? Every tangent vector is represented by a path, right? So one way of thinking about tangent space is the set of equivalence classes, the space of equivalence classes of paths through a given point, right? So now, if you have a path on a group passing through an element E, and any element, another element of the group G, you can just use left multiplication by G to move this path, right? What is a path? A path is a map from an interval to your group. So let's take the composition of this map with a left multiplication by G. So under this, so this is my map L sub G. It takes this path to this path. So if I have a path passing through E, I can construct for any G a path passing through this element small g, just by using translation. That's how you construct all invariant vector fields. So now I claim that if you are on a real line, if you translate this vector field, right? If you translate it, you still get a linear path. So it's definitely translation invariant. Okay, so this is one example. Another example, example 2, is let's take for G the multiplicative group of the real numbers, all non-zero numbers with of course with product operation. Okay, so in this case, the again I look for invariant vector fields. Vector fields. So I want to describe them all, right? And well, G is a subspace as a manifold. It's a subspace in it's a open subset of R, right? So I have coordinate here, right? So every vector field can be written as a function times d over dx. So d over dx times a function. And I want to understand which of these vector fields are invariant under the map that takes x to c times x, where c is any number. So if you substitute here c times x for x, this vector field gets divided by c. So it's not going to be invariant. In order to get an invariant vector field, you can multiply it by x, right? Then when you replace here x by c times x, well, you get the same vector field. So this is an example of invariant vector field. And if you want to get all, well, you know that it's one-dimensional vector space, so you can just multiply it by any constant, and you know that you'll get everything, right? Very good. That's another example. So, and lastly, example 3, which is in fact a generalization of example 2, but it will be kind of sort of less explicit. So let's take for G, GLN, the group of invertible matrices and M-same matrices. Then I will, I could, of course, there is also a chart, a global chart for G. I could think of G as open subset of the vector space of all n times n matrices. So every vector field can be written as combination of, well, so that means that I have coordinates on this manifold, global coordinates, which are just entries of my matrix. So every vector field can be written as a combination of partial derivatives with respect to these coordinates. But I want to sort of, instead of writing it's a combination of partial derivatives, I want to express, describe invariant vector fields in geometric, in more geometric ways. So, so if suppose I have a tangent vector, just one vector, T, E, G. So, so assume that I know that this space, this tangent space, can be identified with the space of all n times n matrices. So, namely, so every tangent vector can be represented by a path if is represented entered by a path. So okay, it's going to be theta array this okay so it takes t to 1 plus ta. It's a linear path. A is a matrix. So this is a path whose value that passes when t equals 0, it passes through the neutral element. This is identity matrix, E and G. Right? So it's equal. Now, so then for invariant theta, left invariant, theta sub g is represented by a path passing through G, of course. So, and what is this path? So you're supposed to take this path, this is a passing on G passing through E, and you're supposed to apply this map L sub G. So simply take this path and multiply it by G. G plus T, G, A. Okay? So, very good. So, and all G invariant, left invariant vector fields on GLN are of this form. Okay. So, and by the way, it's so we talked about, we discussed left invariant vector fields. Of course, there is you can replace the left translation by the right translation. So you also have the notion of a right invariant vector field, and the space of right invariant vector fields is also identified with the same tangent space as the neutral element, though a left invariant vector field need not be a right invariant, right? So a right invariant vector field would have the same form, except that this G and A are interchanged, right? You have A times G instead of G times A. So the vector spaces of global G invariant vector fields, left and right, are isomorphic, though they are not equal as subspaces of the space of all vector fields. It's only true if your group is commutative, right? Then the left multiplication and the right multiplication coincide. That's a very important observation. Okay. So you should keep in mind these three examples, and still I want to give you another point of view on invariant vector fields. So I recall that vector fields, the space of vector fields on any manifold can be identified with derivations, the vector space of all derivations of C infinity G, of the ring of the algebra of all smooth functions on G, right? So let's take a derivation, and let's ask ourselves, what does it mean for a derivation, for the vector field corresponding to a derivation, be G invariant? So what does it mean for theta in derivations So that's the notation that I'm using here, C infinity G. What does it mean? Be left G invariant. Right? So if I have a derivation, I can look at the corresponding vector field, and we have this notion of left invariant vector fields. So I want to translate this concept to the language of derivations. So, and the translation is straightforward. So, so let me just formulate the answer for you. So, so it must be a property of so derivation is a map from functions to functions that satisfy certain properties. So, and I want this map from functions to functions be somehow compatible with the left translation. And that's the most obvious way. Here is the most obvious formula you can write. So if you have a function f, you can translate it through G, right? Diffeomorphism axiom functions, and then apply your derivation. Or you can do it in the other order. You can first apply derivation and then translate. So this is the condition for theta to be G invariant. So it agrees with the corresponding notion for vector fields. So let's. I'm not going to verify this again. This is sort of straightforward. But let me go back to example 2. I will put prime here, right? So G is equal to R prime, R star, multiplicative group. So, and let's try to understand what this condition means, right? So let's find all derivations satisfying this property. So suppose that, well, any derivation can be written as a function times d over dx, partial derivative, where x is the usual coordinate on R star. Okay, so theta is invariant. So, well, this formula holds if and only if the following is true. So let's write down explicitly what it means. So I can if for any function on my group star in this case, the following holds. So I take f, I first apply to this. So f is a function in, say, in x. X is a coordinate on my group. So I first consider a new function. I apply translation. So I get this function. That's still, I consider this g here as a constant. It's just an invertible number. So it's a new function, still function in x. And I differentiate it along this vector field, theta. What does it mean to differentiate it? Well, you simply take partial derivative of this new function and multiply it by h of x. That's by definition the left-hand side of this equality here. So now the right-hand side is the following: you take f, and then you take you apply to f theta, so you get df over dx. Then you multiply it by h, right? You get a function in x, and then you translate it. So that means, so that you sort of, you consider this as function in x, and you substitute, evaluate it at point g times x, right? Is it clear what? Okay, so that's, so this is by definition the right-hand side of this formula. So we want to understand the condition on h, which guarantees that this holds for all f. Well, here we can apply the chain rule, right? So this is we differentiate this function in x, g is constant, so that's this is just g times partial derivative of x of f with respect to x evaluated point g times x. So this condition is equivalent to saying that to saying the following, that h of x times number g is equal to h of gx for all g. Right? So again, look at this formula and observe that sort of partial derivative of f evaluated at g times x appears here and also here, and you can cancel and divide by it and to get this formula. So we are looking at all functions h of x that satisfy this property. And it's clear that, well, so you just plug here x equal to e, so this function is determined by its value at let's say at 1. So h of x must be equal to x times a constant. For some a in R star. No, sorry. Okay. So we recover the answer that we already have. So so we have two perspectives on invariant vector fields. Either we can think of them geometrically as just passes which are obtained by translation of a single pass passing through E, or as derivations satisfying this property that they commute. So you have the vector space of all C infinity functions, and the group G acts on functions, and we consider it acts on all functions by translation, and we consider derivations of this vector space, so endomorphism of this vector space, which commutes with all this with translations. Okay. Now this formula, this second interpretation, makes it obvious that if you have two invariant vector fields, if theta 1, theta 2 are left G invariant, then so is the commutator. Okay, so let me, though it's straightforward, let me give a proof. So what do you want to show? You want to show that again this we already know that this is a derivation. We want to show that it commutes with L sub G. Let's just write down. We take a function f, we apply L sub G. Now we apply theta 2 to this, then theta 1, and then subtract theta 2, apply theta 1, apply to L sub G of f. So what happens here? So I take a function, I first apply this operator, L sub G, to this function, and then I apply the commutator of the two derivations. And I want to show that it's the same if I do it in the opposite direction. So, but L sub G commutes both with theta 2 and theta 1. So I can simply write it as LG upper star of theta 1 applied to theta 2 applied to F. Theta 2 F minus theta 2 theta 1 F, and this is by definition, this is the commutator. Theta 1 theta 2 apply to F, and then you apply LG to this. And what you have here is the commutator theta 1 theta 2 applied to L by G. Okay. So this proves the law. Very good. So so let's see what we this is a a very important observation, because what we have now, so we have every group, a Lie group, for every Lie group, we can look at its tangent space at one point, at the neutral element. We can identify this vector space with the space of G-invariant vector fields or G-invariant derivations, which is less understandable object. But however, the latter has the advantage that it has this commutator operation. So in particular, we have the commutator. We get a new operation on this finite dimensional vector space. Okay, so let me recall for you an abstract kind of a definition, abstract definition. So a Lie algebra is a vector space say T together with a skew-symmetric symmetric map, skew-symmetric bilinear and mirror map from T times T to T, such that the following identity holds. So again, this is notation for my map, and the formula, which is called the Jacobi identity, is the following. So if I apply this map to, or if I take three elements, x, y, and z, and consider this commutator here, that's the same as taking first commutator of x and y, and then foreign commutator with z. And then you add to it x commuted with y, comma z. So
I believe it's not true, because we have two identical things right on the left side.
Sorry. This, yeah. Thank you. I will let me. So you take y, and then you take commutator of x and z. Okay, so how one can memorize this formula? So think of, consider the operator, commutator with x. It's an operator from T to itself. And think of kind of commutator of y and z as kind of a product on T. Then this formula says that this sort of commutator with x behaves like a derivation, right? So you first take derivative of y with respect to x here, and then take kind of the product, and then the second part of the Leibniz form. So this is a purely algebraic notion. So here is a sort of two examples to have in mind. examples. Example 1, which motivates this formula. Let A be any associative algebra. Right? Then A together with a bracket defined by the formula xy minus yx is a Lie algebra. Right? That's a straightforward computation from the associativity axiom. And that's sort of, in fact, one can show that any Lie algebra appears as a subalgebra of the algebra of this form. So that's kind of a, I'm not saying that all examples are of this type, but that's very close. Any Lie algebra can be embedded into such. So that's one example to have. Another example in particular, well, you can take algebra of matrices, associative algebra, and take the usual commutator. That's an important example. So example 2, which is very important for us, is you can take the vector space of all vector fields on a smooth manifold, right? Together with a Lie bracket that we discussed. And this is a Lie algebra. This is a very complicated example because this vector space, again, is enormous. So it's always, unless M is zero-dimensional, it's always an infinite-dimensional vector space of real numbers. Okay, so and now, so these are the two main examples. So and kind of the third example, which is the most important for this talk, is well, you can take left G invariant vector fields on G with Lie bracket. So what does it mean? It means that you think of your vector field as well, you forget that it's G invariant. It's just you have a commutator of vector fields on any manifold. So we have a Lie algebra of vector fields on G, and this is a subalgebra. This is a Lie subalgebra. Right? So it's saying that it's subalgebra means that it's a subspace which is preserved under the bracket, and it's indeed preserved by according to this lemma. The purpose of this lemma, the assertion of this lemma, is that the commutator here restricts to a commutator on G invariant vector fields. Okay, so that's the most important example again for us, and this is called the Lie algebra of a Lie group. Okay, so this is the usual notation for the customary notation for the Lie algebra. I look at left G invariant vector fields. Instead, I could look at the right invariant vector fields as vector spaces. They are both identified just with the tangent space at the neutral element. So, but in fact, you get the same Lie algebras. So, so using you can get a Lie algebra structure using left invariant vector fields or right invariant vector fields, and this gives you the same Lie algebras. Okay, on the tangent space at T. So again, as a vector space, it's just the tensor space at T. So it has dimension, its dimension of this vector space is equal to the dimension of G. And you need this interpretation as a left invariant derivations in order to introduce the Lie break. That's a kind of very general, very, well, I think beautiful construction. And again, the main point of Lie theory is maybe I will formulate it as a slogan here. So Lie algebra of G remembers a lot about G. So what does it mean? Well, if you wish a precise statement, I'm not saying that G as a Lie group can be recovered from this Lie algebra. Well, let's see two sort of most obvious examples. So let's consider for G say R with operation addition. Then well, the Lie algebra of G is of course R, is one-dimensional, and the Lie bracket is identically equal to 0, right? Just because it's skew-symmetric. So you don't have much choice on one-dimensional space. Any skew-symmetric form is 0. Right, and it's Z is skew-symmetric. Now, so if you consider G equal to R star, this product operation, the Lie algebra is going to be the same. So this is kind of bad. You cannot differentiate just by looking at Lie algebras. You cannot differentiate these two groups. So, but that's basically all that can happen. So a theorem here is that if you have two Lie groups which are simply connected, then any isomorphism between the Lie algebras extends to an isomorphism between groups. So that's a hard theorem, which is definitely goes kind of beyond the scope of this course, but so it's good to have in mind. Okay, so these are kind of trivial examples. I want to give you something more interesting and kind of a key example, right? Key computation. So let's take for the group GLN. G equal to GLN. Okay, so GLN now.
Excuse me.
Yes.
What is simply connected?
Simply connected means that it has the trivial fundamental group, or that it has no covers. So if you don't know either of this, if either of these two words tell you anything, then just ignore this. Okay. So so maybe let's put it this way. So if you have any group, then it has a universal cover, which is a simply connected group, and the original group is obtained from this universal cover by taking the quotient by a subgroup. So, for example, though these two groups are not isomorphic, the universal cover of R star is going to be R, and the map is exponential. So you have R, you can think of R star as a quotient of another group by a discrete subgroup, namely by Z. This map is this is also not I should say connected, simply connected. This group is also another problem with this group is that it's not even connected, right? And if your group is not connected, for example, if it's finite group, then its Lie algebra is trivial. So there is absolutely no way to recover. So if you can, so in order to have kind of an equivalence by adjunction between Lie groups and Lie algebras, you definitely need to assume that your group is connected, right? Because the tangent space at 0 does not remember, the neutral element does not remember anything about other connected components. So if you consider the connected component of this group, this is positive real numbers, then you can think of these positive real numbers as a quotient of R by sorry, let me say something stupid. Yes, definitely I'm saying something stupid here. This is already, here I have the exponential map, and it's already the isomorphism, right? So what I wanted to say is that there is another example, maybe where the bijection breaks is when you take the group of invertible complex numbers and compare it with the group of complex numbers with so this is, here I have multiplication operation, and here I have the addition operation. Definitely the Lie algebras are going to be, well, this has dimension 2, this also has dimension 2, they're commutative. So the Lie algebras are going to be two-dimensional vector spaces with zero bracket. So that you cannot differentiate one group from the other by looking at the Lie algebras. But what happens here is that, and they also connected, right? But what happens is that though these two groups are not isomorphic, there exists a map, the exponential map, which is now surjective, but it's not injective. So it realizes C star as a quotient of C by a discrete subgroup by Z. So that's up to this taking quotient by a discrete subgroup. Well, Lie algebras recovers your group or your group. Okay, that's a little bit imprecise statement, but I'm not going into details. So instead, so the whole point of this discussion of Lie groups was that it's a very good illustration of the basic notion of differential geometry, namely sort of commutator of two vector fields. And I want to sort of do this computation for GLM. So let's try to compute the Lie algebra. So again, so Lie algebra of G as a vector space, it's this space, and because GLNR is an open subset of the vector space of all matrices, you can identify it, as we did many times, with the space of all matrices. So if I have a matrix A, it gives me a vector field, and I had a formula for this vector field. So let me give first a name to this vector field. I will call it theta of A, and it has, by definition, has a property that theta A, this left invariant vector field, evaluated at G, is represented by the following path. T goes to G plus TGA. That's the formula that we had some time ago, right? That's a path. Through point G. So that's how identification between the space of all matrices and left invariant vector fields on GLN works. So with this in mind, I want to compute the Lie bracket, right? So my goal is to compute a commutator of these two vector fields. Well, as you may guess, I want to recover, I want to show that the sort of the commutator of the vector fields corresponds to taking commutator of matrices. So it's really the Lie algebra of GLN is the algebra of matrices with usual commutator. So let's try to compute this. Well, you can either that's not something difficult. You can just write down how to have global coordinates again. You can look how it looks like on this theta as a derivation and compute commutator of derivations. I want to do it slightly differently using the notion of one parameter group of diffeomorphisms associated to a vector field and the interpretation of the commutator that we discussed last time. So I recall that every one parameter group of diffeomorphisms on any manifold M defines a vector field. If my vector field, if my manifold is compact, then in fact it's a bijection between one parameter group of diffeomorphism and vector fields, global vector fields. If it's not compact, it need not be the case. But so nevertheless, there is a kind of a substitute for this that we discussed in details last time. So I want to take this particular vector field on G, though G need not be compact. Well, this group is not definitely compact. I claim that so for this particular vector field, there is a one parameter group of diffeomorphisms. It's uniquely determined by the vector field if it exists. It need not exist in general. If I take a non-invariant vector field, it will not be, it need not exist. But again, for fields of this type, I will just write down for you one parameter group of diffeomorphisms. So define okay, maybe so let's try to get the formula, right? So if you want to write down a one parameter group of diffeomorphism corresponding to a vector field, it's a difficult problem. You have to solve an ordinary differential equation. But sometimes you can get the answer, guess the answer. So I claim that for any matrix A, I want to define a one parameter group of diffeomorphism of G. So what is this? What are the properties of this one parameter group of diffeomorphisms? You see, I want the corresponding vector field be left invariant, right? I want the vector field commute with left multiplication by elements of G. It is natural to so assume that the corresponding one parameter group of diffeomorphisms should also have this property, that it should commute with left multiplications by G, right? What are the maps from G to G that commute with left multiplication by G? I claim that any map like this is right multiplication by some element, right? So therefore, it is natural to look for phi for the one parameter group of diffeomorphism corresponding to this theta as a right multiplication by some element. So phi A sub t of any matrix, invertible matrix, should be G times something, times a kind of a given matrix which depends only on A and T. What should be the properties of this matrix? So it depends on T, and it should be kind of the basic property is that phi A t plus t prime should be equal to the composition. Right? That's a definition of a one-parameter group. So therefore, this matrix, well, it's actually not one matrix, right? It's a map from R, from real numbers with coordinate t, to matrices, and this map takes sum to product. I know one example of such a map. It's called exponential. Right? So I take matrix G and I multiply it by this. It definitely sort of this map has the property that commutes with left multiplication, and it has the property that, well, by the very definition, it has this property because exponential of, well, because of the property of exponential. Remember that exponential of a plus b in general is not equal to the product of exponential of a times exponential of b for matrices. But it is true if two matrices commute. So for matrices of the form a times t prime, that's definitely true. So this formula holds. So that's almost everything, except that I also need to verify that the corresponding vector field is given by this formula. So I need to compute the derivative of this phi at t equals 0. Well, what is exponential? Is 1 times a times t plus higher order terms. So derivative is simply going to be a. So you get this form. Okay. So then phi a sub t is one parameter group of diffeomorphisms. Corresponding to theta. Very good. So you see, we somehow solve the ordinary differential equation by using that it has many symmetries. That's typically differential equations, unless it's linear, cannot be solved unless you can find many additional symmetries. That's what happens here. So now let's finish the computation. So so let's compute the commutator of two vector fields, left invariant vector fields. One corresponds to matrix A, and another corresponds to matrix B. Right? That's what we want to do. We want to show that this is the left invariant vector field corresponding to the commutator of the two matrices. Okay. So I'm going to use the formula that we had, we proved at the end of the last lecture. So this is the Lie derivative. Sorry, this is not part of the notation. This is the Lie derivative of one vector field with respect to that. And if you do not remember what the Lie derivative is, I will write down the formula for you. So what you're supposed to do, you're supposed to take one parameter group of diffeomorphisms corresponding to this vector field here. And we already have it. This is A sub t. And you apply this one parameter group of diffeomorphisms to the other vector field, right? So this is a vector field which depends on t now, right? And you can take its derivative with respect to t and substitute t equals 0. Okay. So now so we have everything here is very explicit. We have a formula for theta. We have a formula for this phi, and I claim I can compute, in fact, explicitly what is written here. So I will just write down an answer for you, and this is the most important kind of exercise here to, well, homework problem, which is merely a substitution of, well, an exercise on definitions, but still I invite you to do it to verify that what is written here is the following. It's well, it must be a left invariant vector field. So it should correspond to a certain matrix, and this matrix is theta of e to at, b e to the minus at. Okay? So this is what it's written here. Now you take its derivative with respect to dt. And then substitute t equals 0. So with this in mind, it's easy now. So this is you just have to differentiate this this matrix with respect to t, and so what you'll get is d over dt. Let's see. So you have theta of 1 plus a t plus a squared t squared over 2 factorial plus so on plus times b times 1 minus at plus a squared t squared over 2 factorial and so on. Okay, and I'm supposed to take this derivative and plug t equals 0, and it's clear that, well, so the only term that we should look at linear term at t, linear coefficient at the first power of t, which is going to be okay. So there is a term which does not constant term, which does not depend on t, which is simply b. So it's d over t of b. Then I have commutator of a comma b times t plus t squared times sin. And I plug here t equals 0, and so this does not depend on t, so I get theta of commutator of A and B. Very good. So summary of this is that Lie algebra of GLN is just matrices, and commutator is given by the usual formula: AB minus BA. So this is a key computation, and once we have it done, so you can compute the Lie algebra for many other groups. For example, the orthogonal group. Let me finish with another example. Let's consider ON, maybe ONR. So this is the group of matrices here, G and GLN, are satisfying the property that G times G transpose is equal to 1. So so let's compute its Lie algebra. The strategy here is very simple. So let's take this orthogonal group is a subgroup of GLN. And in fact, we discussed last time that that's not only a subgroup, it's actually a submanifold. So okay, so if you, in general, any homomorphism of Lie groups defines their homomorphism of the corresponding Lie algebras. So now, so this this map can be easily described on the level of vector spaces. Namely, this is the tangent space to GL and the neutral element, and this is T E subspace. And what is this map? So which tangent vectors? So you have a manifold, you have a submanifold, and you want to look at the tangent space to the submanifold. So in other words, so how to think of this tangent space here? So what are the passes? All the passes are of the form 1 plus TA, where every path, every tangent vector is represented by a path of this form. So when this path is tangent to the subgroup, when if and only if you take this matrix and multiply it by 1 plus TA transpose, it must be equal to to 1 plus t squared something, right? It should not have linear term. That's the condition that the path is tangent to the submanifold given by this equation. And that's equivalent to saying that A plus A transpose is 0. So that means that this is skew symmetric matrices. Skew symmetric matrices. So now we we have a map of Lie algebras. This Lie algebra can be identified with the space of all matrices with the bracket given by the commutator. And we know that this is a subalgebra here. Well, and we computed this subalgebra as a vector space, but it must be a subalgebra. So this is a map of Lie algebras. So it's a skew symmetric matrices, and the Lie bracket must be the commutator because that's again a map of Lie algebras. So so that means that well, this Lie algebra is just the vector space of skew symmetric matrices with usual commutator. So that's a kind of a general strategy for computing Lie algebra of a group. If you can embed your group into, say, general linear group, then so it induces an embedding on Lie algebras, so you can use the main computation that we have already. Okay, so I would like to make a 20 minutes break here. So we will resume at 6:25. But as I said, so we will have some review of tensor algebra. I don't even think that we will have time to get into our vector bundles. So if you're comfortable with like notion of Grassmann exterior algebra, then you should just skip this hour, the next hour, and join us at next Wednesday. Okay, so otherwise I'll see you in 20 minutes. Any questions? Okay.
I have a question.
Yes.
Left and right invariant vector fields are isomorphic vector spaces. Is it true?
Yes, because both they're isomorphic vector spaces.
Because both
isomorphism is constructed via identification with the tangent space at the neutral element. You have the evaluation map at E. I will write it down. That's a important point. So left invariant vector fields. This is isomorphic to TEG, and this is also right. Okay?
Yes, I see.
More questions? Okay, so if not, then let's resume at 6:25. Okay, so let's resume. The purpose of the remaining part of today's lecture is to prepare some kind of linear algebra background for introducing differential forms, for introducing operations on vector bundles, like tensor products or exterior products of a vector bundle. And so since I have only 1 hour, so it will be today it will be just linear algebra. So a recap. Of tensor algebra. Okay, so the basic notion here is the notion of tensor product. So if I have vector spaces V and say W, vector spaces, say over R, so we shall define a new vector space the tensor W together with a map of sets. Let's put it this way. So for every V and W, put it this way. So V is an element in V, and W is a vector in W. We are going to have a vector in this tensor product. So that is to say that we are going to have a map from V times W to the tensor product, and this map, well, if I have a pair V, W, I will denote its image by V tensor W. This map is not linear. It's going to be just a map of sets. However, it will satisfy certain property. Instead of being linear, it's bilinear. So such that two properties hold. First of all, if I have two vectors, lambda v1 plus mu v2, And if I take its product with W, so this is a vector space. This, for me, is a set. Of course, it has a structure of a vector space, but it plays no role in this construction. Do not consider it just as a set. It's product of two sets. So this is a vector here in this vector space. And the requirement is that it must be equal to lambda v1 times w. So here, this is again a vector in this vector space. I can multiply a vector by a scalar, by a real number, and I can add to it mu times v2 tensor double. And the second property is, well, it's bilinearity with respect to the second argument. So if I have v tensor lambda w1 plus mu w2, it must be equal to lambda v tensor w1 plus mu v tensor w2. Okay, so the construction of the tensor product of two vector spaces, again, produces for you a vector space together with a map of sets, right? This map, which is bilinear in this sense, the property 1 and 2 hold. So, so I will first give you a formal definition of V of the tensor product. And so the idea of this formal definition, the idea of this definition is the following. So I want to kind of solve a universal problem. I want to make a kind of give a canonical, sort of as canonical as possible, construction of a vector space together with this map satisfying property 1 and 2, which is kind of universal, which is so I'll explain what it means. So definition is of the tensor product is the following. So you take you define it to be the quotient. Well, of the vector space with the basis, with a basis given by all elements of the form, all expressions where V is in capital V and W is in capital W. So this is an enormous vector space. So you consider the elements of this basis are numbered by all pairs of vectors in V and in W. So there are no relations here, right? So even if V and W are finite dimensional, for example, one dimensional, this is still an infinite dimensional vector space. So clearly it has a map. We have a map, canonical map, from map of sets from V times W to this infinite dimensional vector space, which takes a pair VW to one of the basis vectors, one of the vectors of my basis. So what are the elements of this vector space? These are just formal sums of expressions like this with real coefficients, finite sums. So almost all coefficients must be equal to 0. That's by definition of vector space with a basis. So this vector space, again, we have a map like this, but it need not, well, it does not satisfy this property, right? Because these are three different vectors of my basis, so they are linearly independent. So the idea is to take this enormous vector space and mod it out by something so that this relation will hold. And it's clear what you should mod it out by. You simply mod it out by the subspace generated by the following vectors. So you take lambda v1 plus mu v2 tensor with w minus lambda times v1 w minus mu v2 w. So, right? So these are definitely vectors here. So you can consider the subspace, vector subspace generated by these vectors. And now you have a map from this set, capital V times capital W, to this quotient here. And by the very definition, it satisfies the first property, but not in general the second. So you should also add the relation, which I will not, well, similar relation with V and rows V of and W interchanged. So V tensor lambda W1 plus mu W2 minus, and I will put dots here because it should be clear what to put here. Okay.
That's a question.
Yes.
When you say the subspace generated by, you mean with all possible lambdas, all possible mu, all possible V1, V2, and W?
Yes.
Okay.
So all these lambda and mu run through all real numbers, and also Vi and W are any elements of capital V and capital W. Thank you for this question. Okay. So now, so I claim that now by the very construction, so the canonical map that we have from map of sets that takes pair VW to V tensor W will satisfy these two properties. Okay? So that's the end of the definition. So this is very abstract, and I find it kind of hard to grasp. And so sometimes in mathematics, the definition itself is not as important as the properties of the object. So for example, when you think about real numbers, it's apparently you don't represent them as in the Cauchy sequences of rational numbers. So the most important property of the tensor product, which is in fact can be taken as a definition, is the following. For me, well, the definition is this, and the property is the following proposition. So the property is the following. So the tensor W has the following I will call it universal property. So I will describe for you what the linear maps from this vector space, be it tensor W, to any other space in a down-to-earth terms. If I have any bilinear map, sorry, this is bilinear form with values in another vector space, to a vector space, then there exists a unique map, which I will call beta, from V tensor W to U, such that B of V W is equal to beta applied to V tensor W. Okay, so B is a bilinear, so it means that it's a function in two variables with the properties that if I fix one variable, for example, W, then it's linear with respect to the first variable, and vice versa. So this is not for me a vector space. I do not consider it as this product here as a vector space. Whereas this is a vector space. It has, among many other elements, elements of the form V tensor W. And so, this property can be pictured in the following commutative diagram. So I have V times W, this is a set, together with a bilinear map to U. And I have this tensor product, which is a vector space, together with a map of sets. And the property is that whenever I have a diagram like this, so this is fixed, whenever I have B, there exists a unique linear map. This is linear. This is linear map that makes this diagram commutative, right? If you go this way, it's the same as going this way. So let's, for a second, imagine that you. So the construction that I explained here solves the following problem. So you are looking, imagine that we don't know what the tensor product is, that I haven't given you the definition, this definition. Then, so we are looking for a vector space such that maps, linear maps from this vector space to U is the same as bilinear maps from V times W to U. So I claim that this definition here is designed to solve this problem. So in fact, this proposition is with the definition that I gave in the previous slide is completely obvious. So
Восьмого, потому без 8 покидаем здание. Сегодня будет дезинфекция.
Sorry.
8 приеду, это только один день.
Okay, sorry for the interruption. So, so how you construct this beta here? So, so this space here is defined as a quotient of a vector space with a basis, right? So, in order to construct a map from V tensor W to something, well, given a map from V tensor W to any space U is equivalent to given a map from this vector space with this basis. So it's just a map of sets from capital V times W to U, such that this subspace goes to 0, right? And so I already have my capital V, this map of sets. So it tells me where the basis vectors go, right? So I already have, there is a unique way, so I have a map from basis vectors, from vectors that form a basis to U, and I can extend it uniquely, right, to a linear map from this from this guy to U. And now the bilinearity property of V tells me that the subspace generated by all these vectors get sent to 0, right? So this is how you construct beta. Okay, so the proof again is it's completely obvious. So how to use this? Well, so let's imagine that it is a important, well, kind of key example. Suppose you have suppose that you have a vector space V, and you are given a basis. Say E1, En. And also you have vector space W with a basis say U1, Un. Then I claim that vectors EI tensor Uj, where I runs from 1 to n, and j goes from 1 to m, form a basis for the tensor product. In particular, dimension of V tensor W is equal to the product of dimension of V and dimension of W. So that's the claim. And let's give a proof of this. Let's see what one has to prove here. So let's again look at this definition. So my first claim is that V tensor W is generated by VI tensor by EI tensor UJ. So how to see that they're generated? It's enough to express these vectors as a linear combination of EI and UG. So, and this is easy because so any vector in V can be written as combination of EI, and any vector in W can be written as a combination of yes. Sorry. So, and I claim that this is equal in this quotient. It's equal to simply sum AI, BJ, EI, tensor UJ. And in order to do this, you just use these relations, bilinearity relations, many times, right? So, for example, if your first vector is just combination of two basis vectors, then it suffices to use it once. Okay, so so at least we know that almost for free from the definition that these vectors generate the tensor product. A harder part is to show that they are linearly independent. It seems very likely, but still, I mean, if a space or a group, say, is defined by generators and relations, it's usually very hard to show that two elements are not equal, right? You can use relations many times, and if you fail, it still doesn't mean that they are not equal, right? So, okay, so, and in order to prove that these vectors are linearly independent, you may use this proposition here, and here is how to do this. So how to show that EI tensor UJ are linearly independent. Here is the proof. So assume that this is not the case. Sum AIJ, EI tensor UJ is equal to 0. We want to show that all the coefficients are 0. Okay, so let's use some a little bit of linear algebra. So so let's fix some pair of indices from 1 to n, from 1 to m. Then there exists a unique bilinear map, I will call it capital F, from V tensor, from V times W to real numbers with the following property: f of EI comma UJ is equal to 0 if pair IJ is not equal to I0 J0 and 1 otherwise. So of course I should put here I0 J0, right? I0 J0. Very good. So why this is the case? Because any bilinear map is determined by its values on basis vectors, right? So EI form basis here and UJ is basis here. So it's clear this F clearly exists. So okay. So therefore this F I0 J0 defines a map little f from the tensor product to real numbers, right? That follows from the proposition, from the universal property of the tensor product. So let's take this identity, apply f I0 J0 to this identity here. Then, by definition of little f, almost all terms here die, because if I pair ij is not equal to the pair I0 J0, then little f applied to this tensor is going to be 0 because it's equal to f applied to EI, capital F applied to EI UJ. So the only term which does not die here is that has EI0 tensor UJ0 here. So we conclude from this that EI0 J0 is equal to 0. And this completes the proof. So for any, we proved this pair can be, we can take any pair of indices and conclude that all the coefficients here are equal to 0. Okay? That's how you use a universal property. In order to, in general, if you want to show that, say, in a group given by generators and relation, a certain element is not equal to 0, well, the only way to prove it is to produce a map, homomorphism from this group to something, to another group, such that the image of your element in the group given by relations and given by generators and relations is not equal to 0. Producing a map from a group given by generators and relations is to another group is easy because you just have to specify where generators go and verify that relations are satisfied. And that's what we do here. Okay. So that's the notion of the tensor product. A corollary of corollary of the proposition is that if you take any two vector spaces and consider the tensor product and take its dual, right? Consider homomorphisms from the tensor product to real numbers. That's the same as bilinear maps. Bilinear maps. From B to the linear maps V times W to R. So that means that in finite dimensional case, which is sort of the most important for us, will be you can define the tensor product simply as follows. You consider all bilinear maps, right? This bilinear maps form a vector space under addition, right? Sum of two bilinear maps is again bilinear. So it's a vector space, and you take its dual and declare this to be V tensor W. Of course, if they are infinite dimensional, then this definition does not really work, because the twice second dual is not isomorphic to the original vector space for infinite dimensional vector space. So you have to modify it, and I explain how to do it. So, once again, I could reformulate this this kind of example here, right? By saying that if you take tensor product of two vector spaces Rn and Rm, then this is isomorphic to, this is a vector space isomorphic to Rn times M. Well, isomorphism of saying that two vector spaces, finite dimensional vector spaces, are isomorphic is just equivalent to saying that they have the same dimension, and we already computed the dimension. So, so again, I could use this this sort of example. It gives you a complete description of V tensor W, right? It's just a vector space with a given basis, but this basis really depends on the choice of a basis V and W. And it's very important that, so in coordinates, this is just a vector space generated by these guys, right? Freely generated. It's important, however, that we have a coordinate-free definition. That's a vector space whose definition does not involve choosing a basis. So in particular, what we have is that by the very construction, if you have two vector spaces, V and W, we have action of the group GLV. GLV is a group of all linear automorphisms of V. Similarly, we have the group of all linear automorphisms of W. And we can look at the product of these two groups. And this product acts here, right? So, for example, if you combine these two examples, you see that the product of the two general linear groups, one is n times n invertible n times n matrices, the other is invertible n times n matrices, acts here, right? So you have a map from GLN R times GLN R to GLN times M R, right? So the kind of the main point of of this abstract definition that I gave for the tensor product of vector spaces is to have this kind of functoriality, right? So you can write down this map explicitly in terms of, well, matrices. So, well, what you have to do, you have to n times n matrix, m times n matrix. You can write down explicitly n times m matrix, but it will be a mess, and this construction makes this kind of action obvious, right? Okay, so now so having defined the notion of tensor product of two spaces, I can generalize it for three spaces, and I can consider iterated tensor products, right? And in particular, I can define what's called tensor algebra of V, of a vector space. The tensor algebra of V is defined, well, first of all, as a vector space. It's just direct sum of all tensor products. So I will start with k equals 0, infinity, and I take iterated tensor product of copies of V. So this is, well, when k is 0, I define it to be equal to k. So this is to real numbers. This is R plus V plus V tensor V plus V tensor V tensor V, and so on. So this is a vector space. It's not just, it has, even as a vector space, it has some additional structure. It's what's called graded, right? You so you can you see that this is a sum of vector spaces numbered by non-negative integers, right? This is sort of degree 0, this is degree 1, this is degree 2, and so on. But now I claim that in addition to just the structure of a vector space, it has a structure. It has a structure of a ring, actually an algebra over real numbers. So, and I will write it on this slide. So the product. So this is an algebra. Algebra means that it's a vector space together with a ring structure. And how is the ring structure works? So if you have two elements of the form V1, Vp, and you want to multiply it, right, by, say, by U1 tensor UQ, what you do, you just write V1 tensor Vp, and then U1 tensor UQ. So kind of take these two expressions together in the order they are written, right? This is a non-commutative ring. This is a non-commutative algebra. So if you take the product in the opposite direction, it will be a different element. So this is I don't have that many slides. So so an example, if E1, say En, is a basis for V, then T of V can be identified with the algebra of non-commutative polynomials in these variables. Is a free algebra on EI. That means that you consider this, well, as in definition of a free group, you consider just, well, all possible products of these elements and combinations of the products, and you do not impose the commutativity constraint that E1 tensor E2 is equal to E2 tensor E1. So it has a universal property, given a map from universal property of T of V is the following, that if you have a linear map from V to any algebra, this is algebra, algebra. Any map of, suppose you have any algebra A, and suppose you have any map of vector spaces from V to the vector space underlying the algebra A. So just forget the algebra structure. Then it extends uniquely to an algebra homomorphism from T of V to this is map of linear map of vector spaces. And this is algebra homomorphism. Okay, so why that? So imagine that V has a basis E1, E2, En. Then given a linear map from V to another vector space is just is equivalent to given a collection of n vectors in A. So now I'm saying, so this example tells me that this is a free algebra on these generators. So given a homomorphism from a free algebra to any algebra is equivalent again to given a collection of n vectors here. So this makes this property obvious. Okay, so the last another construction which is sort of more important for this course is the notion of exterior algebra, which is a certain quotient of the tensor algebra. Exterior algebra. Of A, of a vector space V. So, well, I will define the exterior algebra to be a quotient of the tensor algebra by an ideal. So let I be a two-sided ideal generated by all elements of the form V tensor V, where V is in capital V. So what does it mean that we have two-sided ideal? So this is an algebra, this is an element, so consider the ideal generated by this element. So it means that I look at the smallest subset in this tensor algebra, which contains all elements of this form, and which is closer than the left multiplication by any element here, and also closer than the right multiplication by any element here, and which is also closer than their sum. Addition. So,
excuse me,
yes.
when you say of this form, you mean this V and this W, or
No, this is very important, that these are the same elements.
V and V?
Yes.
Okay, and so all elements of this form are like lambda V times lambda V, or just WW also. And what do you mean by the elements of this form? Just all pairs of identical.
All elements of this vector space, I consider a vector V, tensor V. Just one vector. Yes?
Okay.
Okay. So, example. So for any V and W in capital V, element V tensor W minus W, sorry, plus W tensor V is in the ideal. Proof. So let's consider V plus W tensor V plus W. So this is an element of this form, right? So this belongs to the ideal by definition. On the other hand, you can derive this. It's V tensor V plus W tensor W plus V tensor W plus W tensor V. So this tensor product belongs to the ideal by definition. This also belongs to the ideal. This also belongs to the ideal. So the sum also belongs to the ideal. Well, the ideal is closed under multiplication by -1, so and also by, so it's closed under addition, and so therefore it's closed under subtraction. So if I take this element which belongs to the ideal and subtract this sum, it's I still get an element of the ideal. So it means that this element, this sum here belongs to the ideal. Okay? So what else belongs to the ideal? So I can take, say, element U, tensor V, tensor W, and add to it U, tensor W, tensor V, and this also belongs to the ideal. Right? Because my ideal is closed, by definition of any ideal, is closed under left and right multiplication by any element of the algebra. So I take this element and I multiply it by U on the left. Okay? So now with this set, I can define the exterior algebra of vector space to be the quotient of the tensor algebra by this ideal. Okay, so as a vector space is just the quotient of vector spaces, and it has the structure of an algebra. Namely, if you have two elements in the quotient, you leave them, choose arbitrary representatives in this tensor product, take the product in the tensor algebra, and then project it to the quotient. And from the very definition of an ideal, two-sided ideal, this is a well-defined operation on the quotient. Okay. So we have a map of algebras from the tensor algebra to the exterior algebra. This is homomorphism of algebras. Any algebra maps to its quotient by an ideal. Let's give a name to this. It's pi. So this is a map of algebras. This is, in particular, it's a map of vector spaces. So this vector space is a graded vector space, right? We have a notion of degree, right? Any element, by definition of the tensor algebra, is direct sum of tensor powers of V. So define the exterior, kth exterior power of V to be pi of kth tensor power of V. Okay, so I want to give a name to this this map. So if I have an element V1 tensor Vp, it's an element of this tensor algebra. I denote its image by V1 wedge V2 wedge Vp. So this is just notation. Instead of this tensor sign, I'm going to use this this operation, this sign, this notation for the exterior algebra. So what are the so in particular we have here relations that V1 V wedge V is equal to 0, right? Because V tensor V belongs to the ideal. So that means that well, any element which belongs to the ideal I maps to 0 under pi. On the other hand, this is precisely. So we also have the relation that V1 wedge V2 plus V2 wedge V1 is 0. It again follows from one of the examples in the previous slide, from this example, from this screen. So more generally, you can show the following, that if you consider any expression like this, V1, V2, wedge Vp, and you subtract from this -1, well, I'm going to interchange these factors here. So I use, so I pick any permutation, V sigma P. So sigma is any element of the symmetric group, any permutation on P letters. And so if I take this combination, -1, raised to the power sine. Sorry, just this just sine of sigma, then the combination is 0. So when p is equal to 2, it reduces to this identity. When p is larger than 2, you can derive it from this identity using the fact that any permutation is a product of transpositions. So it's sort of, you reduce it, you prove it. It suffices to prove it in the case when sigma is a transposition. And then it follows from this. Okay? So, another property that deserves to be mentioned is that, in fact, this exterior algebra is also graded. So this is a subspace here, but I claim that, in fact, this is a direct sum decomposition. So this is sum of V, K, V. Okay. Okay. So let's see what else do I have to say. Yeah, I think I have to stop here. Maybe just one last thing. If you if E1 En is a basis for V, then I have a basis for the exterior product of V, namely then vectors EI1 which EIK, where I1 less than I2 less than IK form a basis for the exterior algebra, for the exterior. In particular, dimension of this vector space is equal to binomial coefficient nk, and it's equal to 0 if k is greater than n. So you have so if you look at the exterior algebra, so it has k in it, it has it has r in it, it has v, it has wedge 2 of v, so on, and the last, the top degree is going to be nth exterior power of v. So dimension here is 1, this is n times n minus 1 over 2, and the top exterior power is again one-dimensional. And then you have zeros. Okay, so I really have to stop here. Thanks a lot for attending. Next time we will sort of extend these operations to vector bundles in order to define differential forms. Any questions?
Where will we have the next homework?
Next homework, I will post it over the weekend and send you over the weekend, and it will be due in 2 weeks.
Okay, thank you.
Thank you. Bye.
Bye.